Hello. Today I'm going to go through the modular arithmetic section of 0 to Monero. I'm just going to include sort of my own commentary as well as a few links and examples that I found useful when I was learning the material myself. I'm making this recording to help me with my own understanding as well as potentially offer another method for people to approach the material. And I suppose just the last note before getting started is to give a quick thanks to everyone who created 0 to Monero. With that said, let's get started. Now, Chapter 2 begins with these words about notation. For the most part, I feel like these are more relevant for the later sections of the book, so perhaps unadvisedly I'm going to skip that for the moment and just go directly to modular arithmetic. And the chapter begins by noting that modern cryptography is essentially founded with modular arithmetic and the modulus operator, where you're going to see that, by the way, written mod over and over again throughout the book, modulo or mod. Um, It also notes that we only care about the positive modulus, or saying our result should be a positive integer. So the positive modulus is the same thing as the remainder that everyone's familiar with. Just whenever we talk about sort of the division that everyone knows and loves, dealing with the quotient and the remainder, um, we're concerned pretty much strictly with the remainder, and we're defining, the C result that we're looking for here as the remainder of sort of a classical division. And we're asked walk through this example of imagining a number line, and if we want to calculate the remainder C of A modulus B, we stand at point A and take steps towards 0, with each step being size b until we reach an integer that is between 0 and b, or we can't take any more b size steps. And that result is the remainder that we know and love, c. And we're given these couple of examples, 4 modulo 3. If we're at 4 and we take a step size 3 towards 0, we arrive at 1. 1 is between 0 and 3, so it is our answer. In the same way, you could take a negative number, negative 5 mod 4. If you take a step size 4 towards 0 as a negative number, we're going to add 4 to it. You take negative 5 plus 4 is negative 1. That's not yet in the range we're interested, so we add 4 again. Negative 1 plus 4 is 3. That is in the range between 0 and 4, so that is our answer. You can just do as many examples of that as you feel comfortable with, but that's the idea. Now, these notes here at the bottom, I'll just let you all read those independently. I won't go through them myself. As long as you understand the representation of numbers in binary, then we'll be able to walk through everything that we're interested in today. So now we're given this formal definition where we're saying the positive modulus for the formula that we were just viewing, the remainder, or C, the modulus we can call it, of A mod B, as is a representation of A equals bx plus c, where c is between 0 and b, and x is a signed integer which gets discarded, that being the quotient. So we then note that if a is less than or equal to n, negative a mod n is the same thing as n minus a. If you just imagine, again, we're taking an n-sized step. So if you're in a negative that's just before 0 and you take an n-sized step to the positive, the part of n that is left is just whatever a didn't take from it. That's all this is saying. Makes good sense if you think about it physically. But moving to the actual operations that we'll be performing of addition, multiplication, we start this section by noting that we want to avoid large numbers. We want to avoid large numbers. We're trying to do all of our computations efficiently and avoid any numbers that are more decimals than are necessary, and that's going to drive a lot of the decisions that are about to be discussed here. We're then given this example of 29 plus 87 mod 99, and we're going to say that we're not allowed variables with 3 or more digits, so we can't just add those directly to 116 before taking the actual value. We're then walked through this process where we say, hey, if you want to find C of that a plus b mod n, where a and b are each individually less than the modulus n, we can follow this process. And this was not particularly intuitive to me the first time that I saw it. Just it's a very efficient and effective way of sort of packaging what I see as 3 separate ideas. And if you kind of take those ideas individually, then I think it just helps make this more intuitive. And yeah, we'll just go through that really quickly. So the first result is effectively what this process is it says compute this little intermediate term, and depending on how large that is versus one of the interior values, then you assign one of these two as the answer. And if we look at this first case where c is just equal to a plus b, this is the same case as just saying a plus b is less than n. When you add them together, they're still less than the modulus n. And on its face, that statement, that's fairly intuitive by itself. If we have two values that add up to 8 and we're taking mod 10, well, the answer is just 8. If we have two values that add up to 15 and we're taking mod 20, the answer is just 15. So this is literally just saying, hey, it's the direct assignment when you're not dealing with numbers that add up to a value that's larger than n. We have the second case, which is a little bit bizarre to get an intuitive sense of, because again, we're using this intermediate computation. But if we sort of imagine it physically, and I have a very professional number line graphic to illustrate this, we imagine you have your base n, and you have a and b, which are individually less than n, but together they add up to this value a plus b, which is larger than n. Well, when we're interested in the remainder, the remainder is what we're saying. We need to take an n-size step out of a plus b and see whatever is left. And so in order to get this length down here, which would be our answer, we take a plus b minus n is equal to c. And we can rewrite that in the same way that we included, x equals n minus a up here. We can just, write that in, and then you get this nice formula for assigning the output, b minus x. So hopefully that makes good sense. So something to note is, multiplication is just repeated addition, and there's a technique called double and add that's discussed here, saying, hey, if we want to use multiplication, the example being 7 times 8 mod 9 is equal to 2, we just view this as repeated addition, and we start to group these pieces up. So, we find out how many groups of, adding 8 to itself do we have. So 3 groups of doing that twice, and then, or groups or pairs. We've got 3 pairs, and then we have a pair of pairs, which we could assign up. But depending on how many of these are, you can just sort of chunk them together, and so that you only have to compute one of these pieces once, and then you can just assign it to the others. And that limits the total number of operations you have to do. It's very effective, especially when dealing with very large numbers. And with that, we sort of get more into the details of the algorithm here. In order to go through this, it just walks through. It says you start by converting the first number, in this case a, to binary. So we take 7 and then we write it out in binary. And we just go through this binary array, and this actually will give us the instructions of how we want to manipulate this value in order to get our answer. So we note that we have this array, we're indexing it 3, 2, 1, 0. So in other words, the 0th place is the least significant bit, the first place is here, the second place, the third place. And we note, the a of 0 is equal to 1, so the first element, least significant bit, yeah. And with that sort of sweep set up, we also initialize a result variable. We set that to 0, and we get a sum variable, and we set that to the other value that we're multiplying by, in this case 8, but again, it's just the other. And then we walk through this process, where for every index of the binary value, we test it, and if it's equal to 1, we perform this add operation, and whether it's 0 or 1, we perform this double operation. And you just step through it and you get your final result. So write out in its entirety this early example here on the next page. In the same way, I have an example in Python that I'll use just to go ahead and walk through. I started, by the way, with a Python library, which I'll include the source for in the description. This will come in useful later. It has all of sort of the basic operations that we'll be talking through as you go through 0 to Monero. But for the moment, let's just concern ourselves with these additions, and these are my additions here at the end. The first being the double and add technique. I should show this here just next to the actual process itself. So here's the Python code to represent this. You set up the R value, the S value, and then you're going to just kind of loop through all of the different binary values and, set up those steps and then return it. It's got these comments to the side of it saying which step is being performed where. But just to check that, now let me get that out of the way. Just to check that, I have a version of this included, which just has a bunch of print statements so that we can sort of view the values as this is being executed. And if we go through that code, oh, that's not good spacing. Hold on. There we go. And you can just see these numbers reflect the calculations here. So that sort of demonstrates it step by step, going through it. There you go. Now, in the same way that we have double and add, when we move on to exponentiation, that's just repeated multiplication. And so sort of the same rules apply if we want to go through this process. In this case, it's a technique called square and multiply. So a to the eth power, mod n, we just take the exponent, we rewrite it in binary, and we initialize our results to 1. And in the previous example, we had our sum variable. This test we have our multiplication variable. Just set that to the a value. And then we iterate through using the binary to tell us how we're going to manipulate the value to get the result. You can see sort of the same thing here. We're given this example of 8 to the 7th power in order to test this. And if we go back to this code, we'll just go ahead and take this little chunk. So again, we have square and multiply right here. This is the Python representation of this process. You can see the steps again. They're marked extremely similar in terms of the setup and the execution. And then we have the actual process down here. Let's save and execute, and you can see 8 to the 7th power, mod 9. We're getting equivalent to 8. I guess that doesn't give us the answer directly in 0 to Monero, but if we want to check that, we can just go, 8 to the 7th, mod 9, and there we go. So we can be fairly confident of the process there. You might ask yourself at this point, why is it that writing a number in binary gives us the instructions for how to manipulate it in order to get the result that we're interested in, and why you would use that technique at all? An interesting thought is sort of how to do the fewest number of manipulations necessary to get our result. And it turns out that writing a number in binary actually is a very effective way of doing that when you just sort of consider, hey, all we want to do is go through a process where all you're going to do is double and add, or all you're going to do is square and multiply. It's a very effective way of writing it all out. And if you're interested, I'll have, again, another source in the description to kind of walk through the process of how that actually emerges from the binary representation and goes through it. But essentially, yeah, it's just a very effective, very computationally effective way of getting the answer you're interested in. So with that done, we then now arrive at the modular multiplicative inverse, and this is just a representation of 1 over a value mod n, or the same thing, to the negative first power mod n. And this is very different, or it will return values that are very different from what you might expect if you're used to just looking at a fraction and assigning it a value in other systems. We use this handy definition of the inverse being whatever you take something and you times it by its inverse, and you're going to get 1 as the result. And so, 4 times 1/4 is equal to 1. 5 times 1/5 is equal to 1. 10 times 1/10 is equal to 1. These are all values and their inverse, and that's how it's defined. And we go through this process where we're looking at, okay, we want to get our remainder, our modulus for an inverse value, mod n. We can sort of set up this system. Again, you multiply both sides by a, you get AC is congruent to, you can kind of think of that as equals to, but congruent to 1 mod n. And that places us with C in the range between 0 and n. and for a and n relatively prime. So they don't have to be completely prime numbers, but they can't share any divisors except for one. So if you write out a over n as a fraction, you're not going to be able to reduce or simplify it. As long as you follow those rules, that's what actually allows a modular inverse, modular multiplicative inverse to exist. So the technique that we're given now is using square and multiply to compute the modular multiplicative inverse when n is a prime number. And we can do that because of Fermat's little theorem. And that, anytime that you see a theorem, I know there's a little bit of nervousness that might come with that. Again, I'll include a video in the description to kind of walk through the early understanding of that. But really all it's saying is that when you take this simple manipulation of Fermat's little theorem, where we multiply by a for this equation, and we just take that as a given for the moment. We can then divide out a once, and this again is what we're interested in defining, right? This is what would be the modular multiplicative inverse of a, and we can just take that as equal to a to the n minus 2. And with that, you can actually write code that will very directly, very easily define that value. So if we take this first example I have here, this is just using a built-in Python function, POW, just raising something to a power, and it also allows you to perform the modulo operation on it. So 5 to the q minus 2 power, mod q. For the moment, let's not worry about what q is. It's a very large prime number, and just sort of illustrative of how this may work. So we're going to calculate what the inverse actually is, and we'll print that out. And then in order to check that the inverse is actually correct, right, we should be able to say, oh, well, the inverse of 5 times 5, right, 1/5 times 5 equals 1. We'll just go through the process of actually checking that the inverse is actually true to make sure that it actually returns 1 at the end of that process. So let's do that now. And with that done, here we have our result. So again, division, if you're used to just assigning values to fractions just by looking at them, this is going to be kind of bizarre. But 1/5 mod q, it's not 0.2, it's not close to 0.2, it is this behemoth right here. And that has to do, again, q is a very, very large prime number. It's actually 2 to the 255th power minus 19. That's a useful number for Monero specifically, but we'll get there later. But anyway, just to double check that result, we see again that 5 times 1/5, I should have included mod q there, but anyway, yeah, just taking that result and multiplying it by 5, right? Here's the result, times 5 mod q does in fact return 1. So that's a helpful note and a really interesting cut. And in the case where we're using the built-in Python function POW, it's really nice that we can see that that actually returns that value. But we don't, this function is still kind of a black box. We don't know what was going inside there. But we can do the same thing using the square and multiply method that we just discussed. And in this case, we do actually know exactly what was done, right? Square and multiply, you just step through that process that we just discussed, and it returns the result. And if you want to check it, this is the same value that was returned by the Python library. Again, it's that is the answer. So it's nice to be able to apply that and actually appreciate or realize the steps that were taken. Now we have this note here directly below our example where they say, you have the extended Euclidean algorithm can also find modular inverses, and they have it written out here in its completion in this footnote. I also included that in the code if you want to mess around with that, but because it's just a footnote, I'm not going to worry about it anymore here. So we now go to this section on modular equations, where we take an equation where we're interested in the answer C of 3 times 4 times 5 mod 9, and computing this, you don't actually have to take 3 times 4 times 5 individually in the same way where previously we had two numbers but we didn't want to just add them up directly. So we're developing techniques for ourselves so that we're never going to deal with having to fully evaluate this expression. What we do is we can chunk this up into you take mod and you apply it to the parts individually before actually throwing them together. So in this case, we can take 3 times 4 as one part, 5 as another part, and then we're doing our base 9. We chunk out 3 times 4 mod 9, so 3 times 4 is 12, mod 9 is 3, 5 mod 9, that's just 5, and then we can perform that singular multiplication. You get 3 times 5 is 15, mod 9 returns 6, which is our answer. And you can do that same thing, or at least you can use that as a reference, I guess, for how modular subtraction would work. It's a minus b is the same thing as a plus minus b, and just apply mod in all of those cases. And you can see again, you can just go gangbusters with it if you want. Any sort of definition, however you want to do it, you just chunk it out, you apply it to the parts individually, and as well to the overall answer, of course. It's something you have to do each step of the way. But oh, and he does include, yeah, a nice note on congruence. Why we're using 3 lines to sort of declare this equivalence rather than just the 2 that you're used to. But with that said, we've gone through all of the modular arithmetic operations. We could call it done here, but I'd like to add on a little bit extra at the end. I think it's useful whenever you learn something to actually apply it. So we'll go through this process. I'm going to do a little bit of sort of skipping ahead to grab some things out of elliptic curve cryptography, or the section on elliptic curve cryptography, so that we can do an example that's sort of immediately relevant to the rest of Monero. But yeah, if the code or anything like that seems overwhelming or counterproductive, then feel free to skip the rest of this. But if you're interested in using this, I'd like to go through a little presentation I call Getting to the Point, which is just we're going to go through and use the techniques that we've learned to actually find the coordinates of the generator point that is used in Monero. And that point is defined, you can see here in these notes. I'm just going to kind of follow these here. Go down to what is text page 21 for a definition of what this generator point is. So we have implementations of ED25519 such as Monero typically use a generator G, which is defined by the coordinates unlisted x coordinate and a y coordinate of 4/5. Now, just pretty much ignore all the rest of this. It gets kind of hairy, and that'll be its own thing to tackle. But we're given y is equal to 4/5 or 4 over 5 mod q, again q being this very large number, 2 to the 255th power minus 19. So we're given the y coordinate directly, and then if we look here to a different portion of the page, this is the relationship between an x value and a y value. So we can just use 4/5 to define y, or 4 divided by 5 I should say, to define the y coordinate, and then we can follow through this formula to define what x squared is. The thing is, we don't want to just find x directly, because in the same way that division or fractions in modular arithmetic is sort of bizarre, finding the square root of something in modular arithmetic is also bizarre, and you can see how bizarre it is right there. But again, that's something to be dealt with at a different time. What we can do is just find x squared with this formula. By the way, the d here is just a coefficient. This isn't some kind of calculus thing, but we can just define x squared, and because the x and y values for this generator point G are strictly defined, we can just sort of cheat and use the answer that we know we should get, square it, and then check it against what we've computed. And as long as that comes together, well, we know that we've done the correct thing. So with that, I'm going to actually pull up the reference here. Let me see, do they have a link to it? Oh, here. I'm actually interested in citation 75. And if we go in here, this is sort of the formal definition of the curve that we're interested in, and the mathematical basis of it, and manipulation for it. We get to all of this. Now here, that generator point in 0 to Monero is called G, here it's called B, and we have these coordinates, right? X and y coordinates of this point are these very large, very interesting numbers, and we want to make sure that we get there. So that's how we'll double check ourselves as we go through. But let's first just take a look. This library that I have, it's already defined for us. Like we were saying, oh boy, let me get back to where we were at. Oh man. All right, this went a little off the rails. Let me we'll get there. We'll get there. So this relationship between x and y coordinates, we had mentioned d is just a coefficient. That's already been defined for us elsewhere in this library, so we can also see where that's computed. The actual value is, again, this fraction, 121,665 over 121,666, and the negative value of that. So we can see here in this library that was already defined. Through some of these other points, we can see here's q defined, a few of the other relevant values. Here's d, again using the inverse of 121,666, a few other things, but we'll just go through and go through that process ourselves. So first thing, we can just sort of print up what those values will look like as defined by this Python library by itself. Let me rearrange my windows here just a moment. So we know, or at least we should believe, these are the answers that we're going for. With that noted, let's first find y. So again, we were in the generator point, we weren't given the x coordinate directly, but we were given a form of the y coordinate, and that was 4 divided by 5, and that's going to be mod q. So in order to do that, we need to find what 1/5 mod q is. Believe, again, that's the example from earlier, and then we just multiply that by 4. So we can do that by using the built-in Python function POW, again, 5 to the q minus 2 power, mod q, from Fermat's little theorem. Or we can do that using our custom little process that was detailed right down to every little thing that you're going to be doing here. The square and multiply method from 0 to Monero, so 5 to the q minus 2 power, mod q. And once you've calculated 1/5, you just need to multiply that by 4, again mod q, and then return the value. So let's see that result. Oh boy. Need to change that up. There we go. So there we see the y coordinate as defined by the library itself. We find it using the built-in Python method, and then here's the value that we found using square and multiply. And it's nice to see they all match up. So there we go. There's the y coordinate of the generator point used in Monero. It's nice to see. So with that, let's go on to find not the x coordinate itself, because again we don't want to deal with a square root, but let's find x squared. And in order to do that, we had that formula, right? Y squared minus 1 over, and in this case I'm kind of writing it as like times the inverse, but over d times y squared plus 1, all of that mod q. So we can break this up into finding what the denominator is, the inverse of the denominator in this case, and then the numerator. We'll handle those separately and then multiply them together at the end, again, mod q. So we have this item d, which is just that fraction that we looked at earlier. We can use the square and multiply method to find what it actually was. We say 121,666 to the q minus 2 power mod q. And then we just take that and we multiply it by negative 121,665. Take that mod q, and we'll have calculated d. From there, we can calculate out the entirety of the denominator, right? We need d times y squared, so d times y plus 1. Take all of that mod q, and then in order to find the inverse of that denominator, we then do the same thing where we use square and multiply. So the denominator to the q minus 2 power mod q, and then we will have returned the right half of this equation. In the same way, the numerator, well, it's quite a bit more straightforward, right? We already have our y coordinate, so you just take the y coordinate squared minus 1, so y coordinate times the y coordinate minus 1 mod q, and we can then just multiply the numerator and the inverse of the denominator, again, always, 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 always mod q, in order to get what the x squared value should be. And then we can sort of cheat, and we can use the provided x coordinate that we have here, and we can just square that mod q and check these two values against each other to see if we've got the same thing. And if we go through that process, I didn't actually label it, but here we have not the x coordinate, but x squared. And this x squared value, it matches up whether we're just taking the actual x coordinate and squaring it, or if we're calculating it through the process that we are given from the y coordinate. And that's good confirmation. That's what we've done is correct, that we've set things up properly. So if you've made it to the end of this presentation, thank you for your attention, and I suppose congratulations. You've now learned and applied the fundamentals of modular arithmetic. So cheers.